So they'll be by here, and then we'll just tell them to go away. But sorry about that. Let's make sure that this is actually live streaming here now that we're started. Bear with us at home if you're watching. Okay, good. All right, so just wanted to follow up on the presentation on Friday with a more illustrative example, like a more substantial example of the 0-1 knapsack problem. And so what I did is I went back and I tried to find an old implementation. I couldn't find one, so I just threw one together really quick. I'm not going to show that here, but I am going to show this is the example that we had in class with only 5 elements. And then I went through our test cases and I found one that was moderately large. There are 13 elements in it with a capacity of 15 here. And then the weights and the values here. Now note what I've done here is I've burned the 0 index on this list because as we presented the algorithm, items 1 through n, right, we use the index 1 through n. And so I'm just burning the first element here and burning the first element here. Let me go ahead and run this so that we can take a look at the actual example. 310, all right, Python, knapsack demo, there we go, all right. And it outputs a table that looks something like this. Remember, on the left side here, we've got the elements, and on the right, and on the columns, we've got intermediate weight capacities. And so I've got that over here. So for example, the one that I want to focus on here is this guy right here. Right? So what happens when we consider elements 1 through 6? Right? I'll go ahead and even actually highlight that. 1 through 6. Right? And with an intermediate weight capacity of 8. Right? 1 through 6. Right? Because this is item, remember we're using 1 index in here. A1, A2, ... A6. Right? This is nothing. This is the empty set right here. So, for example, why are all these zeros? Because if you don't take anything, then the value is 0 because you haven't taken anything, regardless of your weight capacity up here. So these are the weights. And because W is equal to 15, that's the one that we're interested in over here. And down here, this is our final solution that we're interested in. What I wanted to do, though, is I wanted to take a look at an intermediate solution here. So this particular one right here. How do we get that 90 right there? Okay. So to understand that, let's go ahead and walk through the actual input first of all. Let me see. I've got my scratch over here. There we go. So again, the interpretation is that those are that we've got 13 items. The weight vector here is that the first item has a weight of 5. The second one has a weight of 3. Then a weight of 8, 9, 7, etc., etc. Right? And we've got values 22, 55, 36, ... Okay. And we've got our capacity here of 15. That's the overall capacity. Now what I want you to do is consider the following. What is the value of V sub ij when I and j are equal to 6 and 8? So V sub 6, 8. That's that entry that I was highlighting right there. Right? This entry 6 and 8. How do we get that one right there? Okay. All right, so the interpretation is as follows of that value. What is the optimal solution value involving elements A1, 2, 3, 4, 5, and 6 with an intermediate weight capacity of 8 here? So now immediately you can see, can I take all 6 of those elements? 5 plus 3 plus 8, that's 16, plus 9 is going to be 25, 32, 33. Can we carry things that weigh 33 if we only have a weight capacity of 15? No. So what we're talking about is some subset of those elements. Okay. Now to understand that, we're going to consider a previous optimal solution. We got it fixed. The solution was to auto setup.
Okay.
All right.
I probably just got on the wrong input. I would suggest putting that in the drawer because I think teachers
Yeah, he was going back and forth. Okay.
Yeah, thank you.
Thank you. That's the same suggestion I made in the other room when they screwed that up. I just took the batteries out so that they couldn't screw it up again. Once I had it working again. So, anyway, we're going to consider a previous optimal solution involving just the first 5 elements. Now, same situation here. I can't grab all 5 of those elements because I would be over my weight capacity of 15. But we're going to consider the same weight capacity of 8. Right? In other words, the best possible solution has value v sub, I don't know why we're dropping frames here, but hopefully it gets better. V sub, let's see, 5, 8. There we go. So that's the entry 5, 8. So all we need to do is come over here to our table and look that up. 5 and 8, 77. Well, hopefully you can see really quick what elements make up or give us a value of 77. Right? Best value is going to be 77. So that's items A1 and A2. Right? And our observation here is that the weight is 8. Right? In other words, we're at the intermediate capacity. Right? If we can only carry 8 pounds, and we only consider elements 1 through 5, then the best that you can do is 77 by taking the first 2, 22 and 55. Right? Try it out. Right? I've got these highlighted here: 5, 3, 8, 9, and 6. Right? Now can any other combination there at most 8 pounds, right? You can carry at most 8 pounds. So 5 and 3, well, that sums to 8. Well, you could take the third item, right? And you'd be at your capacity, but that's only worth 36. Can you take item 4 at all? Nope, because again, your intermediate weight capacity is 8. You could take the 5th item, which is worth 10, but then you can't take anything else. Okay? So the best value so far among those things is 77. Now we make another consideration. Consider taking a sub 6 instead. Right? If we don't take it, then we have the same solution. Right? We have A1 and A2. In other words, like this. We take A1 and A2, and V sub 5, 8, that has the same basic value, right? So in other words, we're only looking at I minus 1j. With respect to that table, all we're doing is looking up one level here, 77, right? In other words, we're not going to, if we don't take it, then we simply just take this value and copy it down. That's how we got all of these, right? When we only considered A1, then you'll take it, 22. Now you're considering A1 and A2, take them both, because you can, right? You can take that they sum to 8, and so you can afford to go ahead and go to 77. But consider the next one, consider the next one, consider the next one. You can't add anything more to that optimal solution. And so each one of these things got copied down, copied down, copied down. But now we do have a choice, right? What if instead we took A6? Again, if we didn't, then we're still at the same solution. If we do, right, then we need to get rid of something else. Right? Why? Because we're at that weight capacity of 8. We need to, if we do make the choice of adding 6, 1, 2, 3, 4, 5, 6, the weight is 1. We cannot go up to 9 yet, right? So in other words, if we take that thing, then we have to throw some other things out. By taking that thing, we're now down to 7 pounds, right? So that's what we look at, right? If we do, we have to get rid of something. Adding A6 means that we have an added value of plus 35. Right? Where did I get that, by the way? Plus 35 right there. That's the value of the 6th element. Right? And then we have reduced our capacity by the weight of A6. There we go. Like this, right? Which is 1, right? So the new weight capacity is 7. How did we get that? Well, we have a weight capacity of J. We subtract off the weight of 6. It was 8 before, minus 1 gives us 7. Right? Then now we're interested in the subsolution. What is the best subsolution involving those things? Right? I minus 1, so elements 1 through n, 5. J minus Wi, that's the reduced weight capacity here. That gives us V sub 5, 7. When we look that up in the table, 5 and 7, we see 55. That corresponds to taking the second element. So taking the second element plus the sixth element, is that better than what we've done so far? Our new solution, our new potential solution that is A2 and A6 with weights 3 plus 4, 1, so 4. That fits within our knapsack of 8. But now the value is 55 plus 35, 90. Is that better than not taking it, which has a best value of 77? Yes. So we end up choosing that, choosing to add A6 to our solution. 90 is better than 77, so we choose to add, to include A6. Right? And as a consequence, column 8 changes from 77 to 99, indicates that we took that item. Right? Now, the solution, the full solution is down here, right? I want to see how we, formulated that solution. So let me go ahead and track this all the way back. So our best solution here is 236, excuse me. We look at the one immediately above that. It's a different value. So what do? We take the 13th element, right? That reduces our weight capacity. What was the weight of the 13th element? 3, right? So consequently, we have to go back 3. 1, 2, 3. And now we're at 12, right? I look at the one above that. There's no change, right? So I go up. I look at the one above that. There is a change. That tells me that I did not take element 12, right? It's not here, but that I do take element 11, okay? Element 11 has a weight of what? 3 again, and so we have to go over 3. 1, 2, 3. We now have a weight capacity of 9. And again, I look above. Did I take element 10? Yes, I did, because these two things are not equal. Right? Element 10 has a weight capacity of what? 13, 12, 11, 10, 13, 12, 11, 10, 1. Right? And so we go over 1. I did not take 9. I did not take 8. I did not take 7. Or, sorry, I did take 7. Undo that. Right? I'm at 7 now, and I'm looking at 6, and so I did end up taking it. 7 has a weight capacity of what? I'll count from the other end. 1, 2, 3, 4, 5, 6, 7. 4. So I go over 4. 1, 2, 3, 4. There we go. I did take 6, right? Because these are different. These are not equal. 6 has a weight capacity of, or a weight of 1, 2, 3, 4, 5, 6. That's the one that we just looked at, right? Of 1, and so I go over 1. And then I'm not taking until I get to 2. There's a difference between that and 1. That gives me 2 right there. Right? So my decisions along the way to take something or not take something were implicitly recorded in this table as I went along. Simply just backtracking will allow you to formulate the actual full solution here. Okay. On the web grader, I think that these tables, these entire tableaus are printed out for your information. You don't have to. You should definitely report a total weight and a total value to make sure that they match. It is okay if you find another alternate solution that has a different weight as long as it doesn't, violate the capacity, but the same optimal value. Okay. All right. Any questions on that? Okay. Then let's go ahead and get rid of this entirely. Get rid of that, get rid of that. And let's talk about the last part of this, let's see, markdown, there we go. The last module that we have for this course, which is computation. Okay. There we go. So my opening question here is, can computers solve anything? Not yet, not yet. What about 1,000 years from now? Will computers be able to solve anything? Star Trek computers now. All right. So consider the following statement. Right? Algorithms solve problems. Right? So another alternative way of saying can computers solve anything is, can algorithms solve any problem that you can come up with? Now, the first one, this statement is a plain old English, right? I'm using dictionary words to define this statement, right? That's not going to cut it for mathematics, right? Mathematics, you can't use the plain old natural languages to talk about mathematical proofs, because if you do, you fall into traps. Have you ever heard of Russell's paradox? Russell's paradox with respect to set theory. Basically, if you're just allowed to use any old words that you want to define what a set is, then paradoxes happen. You can define a set recursively, self-referentially, such that it both contains itself and it does not contain itself. Right? We don't like paradoxes. That's Russell's paradox. So we don't like plain old English when it comes to our mathematics. Right? We need a much more rigorous definition of what these things are. For example, algorithms. What is an algorithm? Does anybody have a nice definition for what an algorithm is? A solution? Okay. A solution to the hunger problem. Is that an algorithm? All right. Make food, feed it to people. Right? Yeah, sure. We could come up with that, but that problem is much bigger than just that kind of solution. Right? So, if you look it up, an algorithm might have a dictionary definition. You could look up Webster's, what that means. You could look up what solve means, and you could look up what a problem means in a dictionary, and you could come up with plain old English statements. The problem is that none of that works for mathematics. For mathematics, you need actual precise definitions of what these things are. And for that, we introduce the following alternative statement. Turing machines decide languages. Right? So now each one of these has an analog here. Algorithms, instead of talking about algorithms from a dictionary point of view, we're going to define what computation actually is, mathematically. Right? And that's a Turing machine. Solve, well, that means decide, and we'll understand what that means once we understand what Turing machines are. Problems. Problems are languages. Now, it's not a language in the sense of English or Spanish or Japanese or whatever. A language is completely different, and it's what we're going to look at today. All right? By the end of this module, we'll have enough terminology and enough mathematical background that we can see that this statement is true. Right? We'll accept that this statement is true, I should say. This is still not a theorem, right? It's the Church-Turing thesis, that what we mean by algorithms, those are Turing machines. What we mean by problems, those are languages. And what we mean by solving, well, that means decide, right? It's a thesis, not a theorem, right? Okay. First of all, let's consider our alphabet. Right? In English, we have an alphabet of 26 letters, right? But in computing, we have an alphabet of 0, 1. Does it really matter that we use a different alphabet? No, why? Well, how is English understood? How is the English alphabet understood with respect to computers using binary? What's that thing called? The ASCII text table, exactly. An encoding, right? So it doesn't matter that we're going to use just zeros and ones in our alphabet. We can take any language if it's Spanish, German, French, whatever, then we can encode it in binary. That's enough, right? A string or word over sigma, oops, math mode here, sigma, is a finite sequence of symbols from sigma. Okay? So for example, we can have the regular old 0 or the regular old 1. Those are words of length 1. We can have other words, right? I could just mash the keyboard here. There we go. There's a word of length 9, it looks like. Right? You can also have words that are just pure zeros, right? That is not the same thing as 0, the number 0. Generally, when we write it out in mathematics, we don't put in leading zeros at all. But when we talk about words over an alphabet, we do, right? 0, right? 0, we could have, 001, oops, 001, we could have 01, right? Et cetera, et cetera. There's a very special word called the empty string, or the word or string called the empty string, right? Which is lambda. There we go. Why do we need that? We need to form a, not a monoid, what is it going to be? Is it a group? Or it's at least a semigroup, right? So in regular old mathematics, you need something called the additive identity. That if you take A plus 0, that gives you back A. That's necessary to define that mathematical structure. Right? What is our operation with respect to strings? With respect to strings, the basic operation is concatenation. Right? Therefore, the additive, here I'll put it in quotes here because it's not really adding, but additive identity is the empty string. Right? That is, if I take any word, for any word, W, it is true that W plus lambda, and by plus I mean the concatenation operator, is equal to W, which is equal to lambda plus W on the other side. In other words, it's commutative. Lambda. There we go. It's commutative. If I add it to either end or any part of the string, it has no effect. Okay? We can also order them, right? The finite strings over a finite alphabet are countable. Right? So for example, I can go ahead and put them in order. Sigma to star is equal to, oops, there we go. I'll start out with lambda, right? Then I'll go 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 0, 0, 1, etc. Right? Now, what order is that? So what's the length of lambda, the empty string? 0. What's the length of these two strings, 0 and 1? 1. What's the length of the next 4 strings? 2. Now look at, so I'm ordering them by length. Within length, how am I ordering them? 0, 0, 0, 1, 1, 0, and 1, 1. By value, we call that lexicographic, right? Lexicographic or binary. If you count in binary, you're counting up, but also if you order them as strings, if you like strings dot sort or whatever, then it will order them that way. Then it will order them in lexicographic order, right? So they're countable. They're infinitely countable. Now we can define a language. Right? A language is a subset of all those finite strings. Right? A language may be a finite set, or it may be an infinite set. Right? But all the members or elements of a language are finite strings. Okay? Now here's our claim. Languages are equivalent to problems. Okay? So for example, an instance of a decision problem involves a configuration of data as input, as well as a yes or no question. Right? For example, given a graph G equals V, comma, E, I'll go ahead and set it up like that. There we go. Is it acyclic or not? Right? You all answered that question by implementing a DFS solution for it, right? Given an integer, x, is it prime or not, or composite? Right? Or something else, like 0 is neither prime nor composite, right? But those are edge cases there, right? So why is my claim here that decision problems, by the way, these are decision problems. Why are they decision problems? Is it acyclic or not? It's a yes or no question. Does it contain a cycle? Yes, it does. Then it's not acyclic. No, it does not. Oh, therefore it's a tree. Right? Given an integer x, is it prime or composite? Right? Is it yes? Is it prime? Yes, it is prime. No, it is not prime. It is composite. Right? These are yes or no questions. You can get rid of the edge cases where 0 is neither prime nor composite, so it's not really a yes or no question, but that's just a technical detail. So again, my claim is that languages are equivalent to problems. Right? So why is that? Does anybody have a good idea? Okay. Well, let's look at the first part, right? Or actually, let's look at the second part here, right here, right? Is it prime or composite? Let's come over here. Well, let's define a language here. Oops. I'm going to define a language to be all x such that x is a prime integer. Right? Tell me, what is this set? What are the, give me a, just start listing out primes here. 2, 3, I got to do all the work myself today. It's 5, 7, all right, at least tell me if I'm wrong. 11, 13, ... So it's an infinite language, right? Well, but that's not my alphabet. My alphabet is binary strings. So you tell me, what's the binary string of 2? 1, right? What's the binary, well, no, that's 1, right? That's 1, 0, right? 1, 0, there we go. What's the binary string of 3? 1, 1. 5? 1, 0, 0. 7? 1, 1, 0. Oh, wait, no. Yeah, I was wrong.
1, 0, 1.
3, 4, 5, 6, 7. 1, 1, 1, 0? No. All right, at that point, I'm going to go ... There we go. I'm going to truncate it. So now, why is this language equivalent to the problem? Right? Given an integer, x, you ask the question, is x in the language or not? In other words, is x not in the language? How does that help you tell you whether or not x is prime or not? If x is in the language, then what does that tell you? If and only if x is prime. And by exclusion, x is not in the language, if and only if, what? X is not prime. Right? That one's really easy to see. Maybe something that's not so easy to see. I'm just going to go ahead and grab a random graph here from the, no, I'm going to draw a random graph. Not a random graph, but A, B, C, and D. There. All right. Now, how could we define a language to ask whether or not is G acyclic? Does G contain a cycle? Well, let's define our language here to be all graphs G such that G is a graph that contains a cycle. That's my plain old English definition of this, right? Now, how can we view that as a bunch of binary strings? Because again, our languages are sets of binary strings. What I'm going to do is I'm going to define an encoding. Right? This is an encoding in binary of a graph G. So you tell me how could you encode this? Well, I'm going to go ahead and use some shorthand here, first of all. My encoding is going to be n, which is going to be the number of vertices, right, followed by a colon here, followed by an edge list. Right? So for example, A is connected to B, right? A is also connected to C. What else? B is connected to C. And C is connected to D. There we go. There's my first encoding. Let me go ahead and cut and paste this. Copy. All right. Paste. Now, is that binary yet? Nope. So what was n? N was 4. How could I encode that in binary? 1, 0, 0, right? Okay. And then a colon. A, B, C, and D, those aren't binary. How could I encode those? I could say that A is equal to 0, 0, B is equal to 0, 1, C is equal to 1, 0, D is equal to 1, 1. Right? Or I could use the full ASCII table if I really wanted to. So now let's encode all that. 0, 0, comma, goes to B, 0, 1, semicolon. A goes to C, so 0, 0, and 1, 0, right? Semicolon. B is 0, 1, and that goes to C, which is 1, 0, semicolon. 1, 0, and 1, 1. There we go. We're almost there. Is that yet binary? Nope. We've got ones and zeros, but also we've got a colon here and a bunch of delimiters. Except that we know that the list is only ever pairs. So what we could do is we could cut this down to one delimiter. 1, 0, 0, comma, 0, 0, 0, 1, comma, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1. There we go. We're almost there, right? What do I do about that comma? Say what? Encode it. How? Is equal to 0? Careful, right? How do I decode that? There you go, right? Encode other encode other symbols with a prefix-free code. That sounds familiar. Where did we see prefix-free encodings? With Huffman coding, exactly. So, for example, I'll re-encode everything. 0 will end up being 0, 0. 1 will end up being 0, 1. And comma here will end up being, doesn't matter, 1, 1. Right? Now, I've blown up my representation, but at the same time, it's all now, I'm not going to write it all out, that's just tedious. But that's going to be all binary. You never really think about that beyond a computer science 1 course, right? Now let me restart it. But you've done this all now for at least a year and a half, right? Here's my knapsack demo. Do you think that it's actually, you know, at the end of the day on the actual hardware, what's actually running on there? Zeros and ones, exactly. It's not a bunch of you know, syntax, commas and spaces and and stuff like that as you would write your actual code. At the end of the day, it's still zeros and ones. Right? So hopefully I've gotten across the point here that all languages are equivalent to problems. Right? In other words, you just have to ask a question about an actual language. Right? So there's the example that we just did. G is such that G is an acyclic graph. All you need to do is encode it in binary, right? You simply need to encode the problem using some binary encoding scheme. We use the shorthand. Now this is LaTeX, so anybody that's doing this in LaTeX, I'll go ahead and type it out fully here. This is Langle, G, Wrangle. Langle, Wrangle are left angle bracket, right angle bracket. They are not the same thing as less than or equal to, because when it gets rendered in LaTeX, it looks like this. Langle and Wrangle. There we go. Right. So it's an encoding, right? This is an encoding of the graph G in binary. Right?
Left angle and right.
Yeah, left angle and right angle, right? It's not going to, LaTeX note here. LaTeX note. Yep, it rendered excellent. LaTeX note, it is not the same as, say, less than G, greater than G. That's what that looks like, right? Because those are the math symbols. Right? So don't encode it, don't write it like that when you're writing this out in LaTeX if you do, right? Given G, does it contain a cycle or not? Means asking the question, does the encoding of G, and for that I'm going to cut and paste Langle Wrangle here, there we go, is that in the language L that we've defined, right? Or not, right? And so we can ask all the questions like this, like just encode it in a binary encoding scheme and ask whether or not it's in the actual language, right? Okay. Here's a technical note, right? The finite strings that are not in L contain encodings of graphs of G that contain a cycle, right? But also encodings that are invalid under whatever encoding scheme that you came up with. For example, the encoding scheme that we came up with here, right? What if I just wrote out a bunch of random zeros and ones, 0, 0, 1, 1, 0, right? Is that in the language or not, right? That's not a valid encoding, valid encoding, so we can ignore it. Right? We could say that it's not in the complement language either, right? Okay. So what other types of problems are there? We've talked about this before, but now we'll go ahead and rehash it because we're going to talk about it in detail. But there are optimization problems, right? So given a graph G and two vertices X and Y, what is the length of the shortest path between them? How did we solve that problem? Do you remember? You just programmed it last week, right? Two different algorithms. There's Floyd-Varshall's algorithm, or just Floyd's algorithm, and it was your Witcher guy, right? Witcher? Dijkstra, whichever one it is, right? That's an optimization problem because we're not just asking whether or not X and Y are connected, right? How do we go about encoding something like this, right? Well, here, let's come up with another one, right? Here's another decision problem. Given G, X, and Y, right? Where X and Y are in the vertex set, does there exist a path from X to Y? Right, squig, arrow, Y. There we go. Right. Nice little squiggly arrow going over to it. Does there exist a path from X to Y? How would you encode that? How would this be encoded? Right. Again, I'm going to use that same shorthand where I've got Langle and Wrangle. Right. And I'm definitely going to encode G. All you have to do is add X and Y. Right. There we go. And does now define a language such that all this language consists of all triples, G, X, and Y, such that X and Y are vertices in G, and there exists a path from X to Y. If there is no path from X to Y, then it's not in the language. How would I encode an optimization problem? The optimization problem is no longer a yes or no question. So let's make it a yes or no question. Right? Encode G, X, Y, and another variable, or another value, K, right?
The shortest path.
Where K is the length of the shortest path. Careful though, right? And ask the question, given Langle, Wrangle, an encoding of G, oops, let me close it off so that it renders, G, X, Y, and K. The question now is, does there exist a path from X, right, squig, arrow, Y, of length K? Now, why does that help us? To find the length of the actual shortest path, you can ask questions over and over again. Ask different questions, right? Ask, is that encoding in the language for 0? Or for, let's go with 1. Right, there we go. So what if the answer is yes? Then you have a shortest path of length? 1. What if the answer is no? Ask another question. Does there exist a shortest path of length 2? Ask, if the answer is yes, then you're done. If the answer is no, then ask another question. 3, right? Dot, 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 right? Just keep asking that question until you get a yes answer. Yes. K, 5, the shortest path is of length 5, and you're done. Right? In other words, the takeaway on this is that optimization problems are no different from decision problems. You can still ask yes or no questions. Right? Sure. Well, oh, okay. Well, that's a good observation, right? What is the largest length of the largest path? Length, the largest possible value of K. Right? If it's a weighted graph, if weighted, the sum of all weights. So you know where to stop, right? You can ask that question first if you want to, right? If the sum of all weights sums to 100, ask, does there exist a path of 100, right? Then go down from there, right? If non-weighted, then just simply n minus 1, right? Because any path longer than that must necessarily be, going over the same edge more than once, right? And if you have a bound, if you have a lower bound of z1 and an upper bound of, say, I don't know, w, let's say, then you can do even better. Instead of asking the question, does there exist one of, this is a classic example. If you've ever heard of what's that game show, Price is Right, right? You have to ask they said, well, this thing costs between $1 and $100, right? And you have to guess the correct price in order to win the prize, right? What do? Do you ask, oh, does it cost $1? No. Does it cost $2? No. Does it cost $3? No. Does it cost $4? No. Like the strategy that I just described right here, right? No, you do a little bit better. So I tell you it's between $100 and $100, and you've got, say, 6 guesses. All right, so guess what it is.
Is it lower than 50?
All right, 50, higher.
Is it lower than 75?
Okay, good, 75. All right, lower. 60. Okay, that's what I was thinking. Yes. All right, you're done. You won, right? What were you doing? What basic algorithm were you just doing? Binary search. Then you can do even better. Do a binary search for the best solution. Right? And That's it, right? Optimization problems are exactly the same as decision problems. Now, there's another type of problem that I'll leave you thinking about here for Wednesday. What about functional problems? Right. Given a graph G and two vertices, X and Y, suppose we already know that there's a path between them. We want a list of vertices that represent the shortest path between them. Right? The output is not a yes or no answer anymore, is it? Just like optimization problems. I want to know the length of it. Well, now I want even more information. I don't want to just know the length of the shortest path. I want to know what is the shortest path. If I go from X to A to B to C, then to Y, that's the shortest path. Right? I want that sequence, X, A, B, C, Y. Right? Can I still do it in terms of a decision problem or not? Right? So, think about that for Wednesday, and we'll pick it up there.